Started. If you remember last class, we had just started talking about classification. So unlike regression, where you try to get as close as you can to the right answer, in classification, you need to label which class your data point is from, and you only get points if it's correct. So close does not count. You need to get it exactly right. And the example I'm going to show you today is something called the MNIST dataset. And these are examples from the MNIST dataset. What is the MNIST dataset? The next slide actually has a little bit more information. They are images that are 16 by 16 pixels, and they are pictures of digits. And what are the classes? The classes are what digit it is. So here are some examples of zeros from the MNIST dataset. There are some examples of ones and twos and threes and so on. And then you're given one of these 16 by 16 pixel images. So it's like an array that is 16 by 16. And your job is to figure out, guess what label it is, what number is written on it. And close doesn't count. So if the true answer is 7 and you say 6, you're wrong. As soon as you're wrong, you're wrong. You need to get it right. Who's heard of the MNIST dataset before? Okay, only 2 or 3 people. The MNIST dataset is like the hello world of sort of like machine learning. It's the dataset everybody sort of uses at first, where things like neural networks are very, very good at MNIST. And sort of classical methods are not as good at MNIST. So we'll start with that. And if you remember, the way we were doing, the first thing we said, one way to do classification is this k-nearest neighbor algorithm. So what would the k-nearest neighbor algorithm look like for this? So you're given some image, and your job is to say, is this a 0, a 1, or a 2, or a 3? How would you do it? And here's a little example. Oh, I clicked on the thing rather than pressing next slide. Let's do that. Okay, here. So here is the example. So here are 2 images, and we can compare the distance between them by going pixel by pixel. So we can look at every pixel and we say how far away are the pixels between these 2 images, and then we can subtract them and figure out, on average, sort of how far would one pixel be from the other one. So what's the between these 2 pixels, what's the between those 2 pixels, and so on. And that gives you a distance function between 2 images. So you give me an image, I have an image in my data set, I calculate the distance, and then I add them all up and square them, and then that gives me the distance. And here are some examples. So here are some example inputs of digits that look like 0, 2, 4, 4, and 9. And these are, in the data set, the closest images. And you can see that sometimes it's quite good. So this 0 found all these other zeros. But this 2 found some 8s and some 7s. So it's not perfect. Okay. And then what we can do is we can do the nearest neighbor thing. So if you do the 7 nearest neighbors, so you calculate the 7 closest pictures, and then you take a majority vote, that is a pretty good classifier. So the 7 closest images to this 2 are 3 2s, 3 8s, and a 7, and so the vote is actually split. Is it going to be 2 or 8? We don't know. We might mislabel that one if the 8s win the vote. Somebody had to do, by the way, to figure out that you should do 7, someone had to do this overfitting, underfitting calculation to figure it out. Okay, is the explanation clear of what does it mean to do nearest neighbor? So last time we did it, it was one-dimensional, right? It was just points, the x value was one single number, and we just did that window thing, But when you have images where the x value itself is very high dimensional, distance kind of means some funny thing. Is the setup clear? Questions or comments about how this thing works? Okay, so if you do the 7 nearest neighbor, you actually get pretty close, 95% accurate. But humans are 98% accurate at identifying digits. So there's sort of, you might think, oh, that's pretty close. We're 2% away, right? 95 versus 97. Pretty close. But actually, there's a huge difference between 95% correct and 97.5% correct. It's really twice. You should think of the error rate. This is twice as bad. We're wrong 5% of the time versus we're wrong 2.5% of the time. So really, this nearest neighbor thing is twice as bad as a human. And not even a sophisticated human like a toddler can, maybe not a toddler, a 5-year-old can look at these and tell you the digits pretty accurately. So this nearest neighbor thing, even though it's using a lot of data and it's calculating the distance to every single thing in the data set, is not doing great. And we're going to learn other algorithms that are a little more sophisticated are doing a little bit better. But the point I'm trying to make here is that nearest neighbors sort of make sense, but should kind of leave you feeling unsatisfied. There's something that kind of bothers me about this approach of how we found the distance. Can anyone think of why this method of doing the distance isn't so smart or isn't so good? Yeah.
It takes a lot of time to calculate.
Yes, that's right. Well, first of all, we're doing a huge amount of operations. Sort of the data is high dimensional, so whatever you're going to do, if you're going to look at it, it might take a while. So yeah, that's one thing. I think the one thing that is quite annoying when you're doing this is not only does it scale with the size of the picture, but it scales with the size of the data set. So I think that part is actually slow, because if you have a huge, huge data set, then calculating this distance between your picture and every single other picture in the data set might take a long time. And you might think, oh, maybe next year we'll have even more digits and we'll do better, but now your thing is slower. So you would prefer a method that as you add more data somehow is condensing the data set and not getting slower when you add more data. That would be one thing. That's true. Anything else? Here is a question. What happens if you take the number 2 and you didn't center it properly? So you shifted it over a little bit. Of course, shifting over a little bit doesn't change the fact that it's a 2, right? Anybody, if you write a 2 over here or you write a 2 over here, they're both 2s. So it shouldn't change anything. What does it do to our distance function? Yeah. Oh well. What do you mean by it shifts it? Yeah. So the whole image will be. This 2. Let's pretend the whole thing was shifted over. Let's say by 2 pixels. Just take this whole 2 and shift it over by 2 pixels.
It's probably gonna totally.
Yeah. It's gonna be like the way we're computing distance pixel by pixel. If you move things over, even 1 pixel is now just some completely different thing, right? And in fact, so you have this backbone of the 2 down the middle, and if those don't line up, then the pixels will be very different. So if I have a 2 that its backbone was over here on this image, it would be like, hey, these pictures are totally different. You have all these white pixels over here, and I have black pixels, and you have black pixels over there, and I have white pixels. So the thing that is kind of silly about this thing is this pixel by pixel comparison. Individual pixels are not the features we care about, right? They kind of are there, we can calculate them, and it sort of works. But at the end of the day, I would like to say something like, you have a diagonal line down the middle. That's why you're a 2, right? But this can't see diagonal lines. It can only see individual pixels and exactly where they are. So you can attempt to fix these things. So here is an attempt. Oh, again, I clicked the thing rather than going to this. So this is a paper from 2009 where they were modifying the distance function. So the distance function would somehow take into account that if you shift it over, it's okay. And so an example they have is, here is a 1 from the data set, and its nearest neighbor before they did anything was this 3, right? And the reason this 1 and this 3 are quote, nearest neighbors is because the 3 has a lot of pixels where that 1 is lined up, right? And I guess other digits of 1, maybe they're a little bit to the left or to the right, and that's why they're not lining up with this guy, and that's why they're not the nearest neighbor. But then they did some training to kind of modify the distance function and to make it better. So after their training, it was this guy, which is a little bit better. So you can try to do this, fix up the distance function. But at the end of the day, this is the same problem we had in nearest neighbors for regression, which is that if your input is high dimensional, it's hard to say which inputs matter, which dimensions are important. For pixels, it's which pixels are important. Well, every individual pixel is not important. So somehow it's the aggregate effect of multiple pixels in a pattern. That's what we're looking for. And k-nearest neighbors is just not good at that. It's not good at knowing which features are important or not. It's only good at measuring the distance between things. Another example that we talked about last time is the scale of things. So you might have some features that go on a scale of 1 to 1,000 and other features that go on a scale from 0 to 1. And if you're not careful with your k-nearest neighbors, you might mix these up. So if you're trying to calculate the distance, how far are you on a scale of 1 to 1,000 versus how far are you on a scale of 0 to 1 can also screw you up quite a bit. So we're going to move away from k-nearest neighbors and try to move into other things that scale well in high dimensional data. That is the moral of the story. So k-nearest neighbors is a very good starting thing, and actually in some applications it can be really, really good, but it does not work well in high dimensional data. And we're going to switch to something that does work well, which we know already is regression. So we're going to try to modify our regression to make it work. So let me write some of this stuff down. Okay. Okay, so KNN, it has some pros and cons. Cons, the pros are it's very general. You can always sort of implement it. General. The cons are can be slow. Well, if you just do it, since finding neighbors scales with data set size. Must look at data set. So if you do something clever to sort of condense it down, then it can be faster, but sort of the naive way, it can be slow. And can be less good with many dimensions for high dimensional inputs. Okay. And so this is the question: which features matter? It doesn't really know how to answer this question. Okay, so we're gonna try to switch to doing like linear operations. I'm gonna say linear estimators. And the linear estimators are very simple. They're a good starting point for understanding more complicated ones. And the idea is, of all the features you can condense down, you can write these like slopes that tell you which features are important or not, or which combinations of features are important. So pros, as it should work in high dimension. Should work well in high dimensions. Okay, and it is interpretable, so you can look at the slopes after. Interpretable, and say which slopes are large or small and figure that out. And the main reason we're actually doing it is it leads to other topics. So to other ones. So sometimes linear regression is not great, but understanding linear regression will help you move on to the next thing. Okay, and so how are we going to do this linear regression thing? So I'm going to start a little table over here. And this is what we did the last few classes. We had this estimator that depended on slopes. So the parameters, we called those the betas. So we had beta 0, beta 1, and so on. I'm just going to write beta to sort of mean all of the parameters. And then we were combining it to get the estimator, which we did beta times x. So x was the input, and then beta times x was the estimate. Before we were writing like beta 0 plus beta 1 x1, you can either think, oh, we're doing a simple situation where there's just x, beta x, or if you want to think like x is a vector, beta is another vector, and we're doing the inner product, then you would get back the other thing. So whichever way you want to think about it. That's what we were doing before, and this was really estimating. This is what we were calling mu hat of x. We were saying we were trying to estimate the mean, the expected value of y given some value of x. This is the kind of thing we've been doing so far. And the question is, how are we going to generalize this? So this was linear regression. We want to try to make something that does classification. How are we going to generalize it? So we're going to have the same parameters, beta, and there's still going to be slopes. But what is the thing that we're going to try to estimate? It's not going to be the mu hat. It's going to be the probability to be in any class. So we're going to try to estimate the probability. I'm going to call that p hat of x, which is the probability to be in some class. Probability to be in some class. And to keep things sort of simple, I'm going to do binary classification. So I'm going to pretend there's only 2 classes. Of course, we just saw an example where there were 10 classes in the MNIST, but we're going to start with binary and work our way up. So p hat of x, and p hat of x is going to be our estimate. This is going to be the probability that you are in class 1. So that's what I want. The probability. Let's say the point x is in class 1. And I'll call the 2 classes class 0 and class 1. Class 0 and class 1. Okay, so that's our job, is to take what we did before and kind of extend it or understand what do we have to change to make it work. Before we were estimating the mean, now we're going to estimate the probability. And we're going to see some things are the same and some things have to change to make it work out nicely. Okay, any questions or comments so far? Okay, so the first thing we got to do, go back way to the beginning of the class. When we were doing this linear regression stuff and estimating the mean, we said we need some kind of method to understand how close our guess is, right? So you come up with some guess for mu hat. The true answer was something else. How do we measure the distance between these things? We're going to have to do the same thing with the p hats. And in the mu hats, it was our old friend, the square distance function. So I have this warm-up mathematized question on the square loss of dice, taking you all the way back to the first few weeks of the course. And you might remember this game. So Alice and Bob are playing this pay the difference squared dice game using some very unusual 100-sided dice. So it's a 100-sided dice, but you should not think that all the sides are equally likely. Maybe some of the sides appear many times. Maybe some of them are weighted. It's some weirdo dice. Alice thinks the dice average is 95. So Alice says, I think the answer is 95. Bob thinks the average is 85. And the true average, which is unknown to Alice and Bob, is 90. Okay? And they're playing this game that we played at the beginning, where you roll the dice, you call the value y, and then you pay based on the difference squared. So if you roll the dice and it comes out 100, then Alice will pay $25, 5 squared dollars, and Bob will pay 15 squared dollars. So depending on what the dice comes up, they pay the square. This was what we did at the beginning of the game. And the question that I want you to answer, whose estimate is better? Is Alice better, or is Bob better, and why? How can you tell who's better? Okay, and there's four options. Alice, Bob, or both are equally good, or maybe you don't know. That's another possibility. Okay, I will give you guys 2 minutes to think this through. Maybe a minute and a half. If it will let me. Okay. All right, 10 seconds left. Put in your final guesses. Who is closer, Alice or Bob? Okay, and let's take a look. Reveal what people said. Okay. One person said Alice, 6 people said Bob, but 16 out of 24 people said they are equally good, and equally good is the right answer. So why is it equally good? You might say, hey, there's not enough information to do this problem because, we know the average is 90, but maybe the dice has some weird skewed distribution where, the average is 90, but sometimes it comes up 1, and sometimes it comes up 100, and it could have any weirdo distribution. So maybe it depends on the distribution. But what we saw earlier in the course is that it depends only on the average, and the only thing that matters is how close you are to the average. That's the only thing that matters, and that's the only way it will affect what you pay on average. So let me record this. This is review sort of from before. Let me record this in our table. This is the loss function. The loss function. And over here, it was the square loss. So the square loss is y minus y hat squared. That's what you actually pay in this game of rolling the dice and doing the square. And then we did a calculation for the average loss. And we found that the average value of y minus y hat squared, it is just the difference between the true mean and what you have. So it's mu hat of, let me not put too much notation. Let's do mu hat minus mu squared plus the irreducible error, which is the variance of y. So in other words, you're trying to get as close as you can squared, but it turns out because of this Pythagoras thing, you just have to make the average close to the true average, as close as you can, and you have this irreducible variance. And the reason I'm bringing all this up and trying to load this into our RAM right now is we're going to now fill in what happens for probabilities, right? What happens when it's classification and you are trying to do binary classification? You have this p hat, and you're trying to guess Is it class 0 or class 1? What is the sort of equivalent way of measuring how close you are? Okay? And instead of just telling you the answer, I want you to kind of puzzle through it. And I have a mathematized question very similar to before, which is there's two types of coins. There's the Alice coin and the Bob coin, type A and type B. The Alice coin is a 95-5 coin. So it's 95% heads and 5% tails. And the Bob coin, the type B coin, is 85-15. So 85% heads and 15% tails. So you have one of these types of coins, but you don't know which type of coin it is. You would like to figure it out. This is a bit like the situation of Alice and Bob. Both have their guesses for what they think is going on, and you're trying to figure out who's better. So Alice thinks it's type A coin. Bob thinks it's type B coin. And then the question is, you see this data. So you flip the coin 10 times, and you saw 9 heads and 1 tails. Which type of coin is better? And this is very analogous to the previous situation, where sort of the true thing that we observed is that it's a 9 out of 10 coin. And is it more accurate to say it's a 95-5, or is it more accurate to say it's an 85-15? So this is the analog of the problem we just did, but in the binary classification case instead of the regression case. So which one is a better guess? So again, you can say they're equally likely. Type A is better, type B is better, or you can say you don't know. So I'll let you think about this one. This is much harder than before because we didn't already do the answer in the class. So let me give you 2 minutes. You might need a calculator or something to puzzle this one out. Which one is more likely? Okay, I'll let you think. All right, just over 10 seconds left. I guess most people have answered already, so that's I will take your guesses and we'll see what it is. Okay, let's see what people said. I'm very curious. This one, depending on how you come at it, there's different ways to think about it that make it harder or easier to find the correct answer. Let's see what people said. All right, beautiful split. Look at this. Not only are we sort of equally split between type A and type B, 8-7, almost exactly the same, we're also a 3-way split with both types are equally like. And of course, only 1 out of 3 of these options is correct. There is some well-defined mathematical way in which one of the answers is right and the other 2 are wrong, and we're perfectly split between them. So I think what we got to do is we got to come up with a framework. The hard part is figuring out how are you going to think about it? How are you going to find out which one is the most likely? Once you kind of have the framework of figuring it out, actually crunching the numbers is not super hard. But the hard part is how are we going to even make sense of this question? Like, what does it mean? Does anyone have a way they thought about it? Like in either of the cases, in any of these 3 options, maybe you had I thought about it this way, and that's why I got the answer that I got.
I think with the 95%, I'm just guessing 9 out of 10 that is going to be heads.
Yeah. Yeah, you're like, so you're saying 9 out of 10 times, that's like 90%. And 95 is pretty close to 90. So it should be the 95, right? Okay, but here's the question for you. 85, famously, exactly the same distance from 90 as 95, right? So this is why it's a hard problem. If it was like 95 versus 80, then I like your way of thinking about it. You're like 90 is closer to 95 than to 80. But in terms of the distance to these things, if you just calculate the distance between the percentages, they're both 5% off. So I don't know how you pick between them if you think about it that way. This is why I made the question. This is exactly to bring up this issue. Yeah?
You use the binomial theorem.
The binomial theorem. Tell me about the binomial theorem. What does the binomial theorem say?
I'm trying to remember back to like high school stats.
Yeah. I think, okay, this is great. I think you have made you're exactly thinking of the right thing. I think the thing you're looking for is the binomial distribution, not the binomial theorem is for a plus b squared, and the binomial distribution is the distribution of flipping many things, which also involves this a plus b squared thing. So like, they're both called binomial because they're related. So let's start with that, the binomial distributions. We're gonna take a little detour from our thing. The binomial distribution, and this is gonna answer the question. When I flip 10 heads or 10 coins, what is the probability? To see exactly 9 heads and 1 tail. This would be the kind of thing the binomial distribution could answer. And the reason this kind of question is tricky, like another question you could ask is, what about exactly 5 heads and 5 tails? So the binomial distribution is called the binomial distribution because it involves this kind of factor of 9 choose 10, or in this case it would involve 9 choose 10. No, 10 choose 9. If we have 10 things, we choose 9 of them. Or 10 choose 5 over here. And this is why it's tricky. It involves these binomial chooses. And it's this kind of question of what's the probability of seeing 9 heads and 1 tail. I will tell you, this is the right kind of idea. The thing is, the question is actually even easier than that, because the hard part of the binomial distribution is there is more than one way it could be 9 heads and 1 tail. Right? It could be a tail on the first one, a tail on the second one. There's a lot of different ways. With only one odd one out, it's not so hard. But if you have 5 heads and 5 tails, there's lots of different ways they could be distributed. So the hard part of the binomial distribution is the order of the different things. And fortunately for you guys, in the problem that was given, I actually told you the exact order. So we've sort of taken the hard part of the binomial is removed. We don't need the probability of getting exactly 9 heads out of 10 tries. We just need the probability of getting exactly this. Heads, tails, heads. Right? So it is related to binomial, but it's like the baby version of the binomial. So let's go back here. So this is the right way to think about it, and this is the right kind of thing that should be percolating through your brain from high school stats. But it's actually even easier. So let's cross out binomial. It's even easier. It's just what is the probability? What is the probability of heads? How many heads did I do? I think I did 7 heads over here. No, 6 heads over here. Tails, heads. 3 heads. So there were 3 heads, 6 heads at first, then a tails, then the 3 heads. So it's an even easier question than this one. You don't even need the binomial. In a different universe where I said I flipped the coins and they came out with 9 heads, then you would need the binomial. But I told you exactly the thing, so it's even easier. Okay, this is a great starting point. What is the probability of this? Who can tell me what is the probability of this thing? So flipping a coin, what's the probability? Okay. This is great. This is the first answer to the question. As with all questions in life, if somebody asks you a question like this, the answer is it depends. It depends. It depends. And I like the way you said it. It specifically depends on which coin. On which coin? Coin. It is. So there's one answer if it's a type A coin, and there's a different answer if it's type B coin. All right. Can you give me either one? This is absolutely the right thought to have, is that this question, you got to tell me what the type of coin is, then I can calculate the probability. Let's do both ways. So what is the type A coin? And let's do the type B. Who wants to tell me what would it be for one of the coins? Any guesses? I don't know, maybe you guys think it's a trick question. I'm gonna like jump on you and devour you if you say something wrong. If I did this problem in my first year probability class, they would all put up their hand and they would have a guess. Some of them would guess incorrectly, but some of them would guess correctly because it's not that hard. I think you're scared or something. What's going on? Yeah.
What, type A?
Yeah.
9 powers of
Type A was the 95% coin, right?
yeah, so 9 powers of 0.5.
Yeah. 0.95, very good. Yes. Yes, what do I do with that?
And like then 9 powers of it.
9 powers of it.
Yeah.
So to the power 9.
Yeah.
Yes. Okay.
Times
Yeah.
0.05.
0.05. Yeah.
I think it's 0.03. I think that's it.
I think that's it. Who also agrees? That's it.
Times 10.
So yeah. So okay. Here's a question. Should we do times 10? Times 10. Here's a question. So let's make the vote like this. Who thinks it's just this, or you think it's not that with the factor of 10? Who thinks it's just this part with no 10s? Okay. 1, 2, 3, 4, 5, 6, 7. Okay. People are getting more confident as they see more hands. 8, 9. 9-ish people, about half the room. Who thinks there should be a factor of 10? Okay, nobody. Who didn't vote? Okay, it's hard to get the people who didn't vote to put their hand up. Okay. You guys are absolutely correct, so very good. There is no times 10. The times 10 would be if the question said, what's the probability to get exactly 9 heads and 1 tails, of which there are 10 different ways that can happen. All of the individual ways are this probability. And this is exactly right. Why is it 0.95 to the power 9 times 0.05? Well, you just have to have 10 things happen in a row, and the things are independent. When you flip a coin one time, you flip a coin another time, they're independent. So you multiply the probabilities. We're doing 0.95 times 0.95 times 0.95 times 0.95 6 times for the heads, then 0.05 for the tails, then 0.95 times itself 3 more times for those last heads. You add it all up, it's exactly this. So this is perfectly correct. Okay. What about the type B coin? Now that you've seen this one, maybe the type B coin is not so surprising. The type B coin is 0.9% heads and not 0.9%, 90% heads and 10% tails. This is that right?
85.
It's 85. Okay, very good. I was like, wait a second. Okay. Thank you for the help. Okay, 85% heads and 15% tails. And if you knew it was a type B coin, then again, you would multiply all the heads together, and then you multiply that tails. Okay. And so it would be 0.85 to the power 9 times 0.15. Okay. All right. This is great. So if it's a type A coin, the probability is this much. If it's a type B coin, the probability is this much. And here is a perfectly nice mathematical way to say, is it a type A coin or is it a type B coin? You say which number is bigger, right? Which number is bigger? Which is bigger? And at first glance, it's actually kind of tricky to tell which is bigger. Okay, this is supposed to be a question. Which is a question? It's like a question that I'm very heated up about. Okay, there we go. It's hard to know which is bigger because look, this one, the 0.95 is bigger. So part of the equation got bigger, but part of the equation got smaller. So like you can't directly compare them and just like look at it and be like, oh, that one, right? You have to figure out which is bigger by typing it in your calculator or doing something clever. It's not immediately obvious. And so now I will let you do it. Let's re-vote on this question. The answer to this question is going to be whichever was bigger. Is it more likely it's a type A coin? Is the A probability larger? Or is it more likely to be a type B coin? Is the B probability larger? And it's hard to know. You got to type it in your calculator and figure it out. Okay, I'm going to re-vote it. It's going up for another minute. You tell me which one is the right one. Let's see. How do I do this? I move this up here. Okay. Oh no. Okay. Okay, it's gonna be open again in a second. Okay, here it is. We're on the revote of is it Alice or is it Bob? And this time I gave you a hint of just calculate the probabilities for the type A coin, calculate the probability for the type B coin, and tell me which number is bigger. All right. Okay, most people have an answer already. That's very good. Let's. Okay, time is up. Let us see what people said. Drum roll, drum roll, drum roll. People said the type B coin is the most likely guess. And I think that's the right answer. Yes, very good. So the type B coin is the right answer because if you go and you calculate this number is bigger. So this number, by the way, this is called the likelihood of the observation with p hat equals 0.85. So in other words, given our estimate of 0.85, which was the type B point, we calculate the likelihood by saying what would be the probability that the thing we saw would happen if we took our estimate as the true thing. And this thing is the likelihood of p hat equals 0.95. So the whole point of this exercise was to get you to come up with this formula for the likelihood that you guys came up with, and you already know from probability 101 is this likelihood thing. And the likelihood is going to be our guide as to what is better or worse and how we are measuring how well we are doing. So when someone says, I've come up with an estimate, and you say, I've come up with a better estimate, what do you mean? You mean my likelihood is better than your likelihood. And this is exactly the same as we had in regression. So remember in regression, we had this loss function, which was y minus y hat squared. And that was telling us how well we were doing. It turned out that the loss function, on average, was mu hat minus mu squared. So it turns out you just want to estimate the mean as close as possible. In estimating these things, we're going to have the likelihood. There is one small little trick that we're going to do before we take the likelihood. And probably you guys noticed this when you were calculating this on your calculator, is that this number is actually really annoying to type into your calculator. Did anybody notice that? And the reason it's very annoying is there's a lot of zeros. It's very close to 0. 0.85 to the power 9 is going to be like extremely, extremely small, like 0.00001, and you gotta like deal with all these zeros. So it's annoying. So there's a trick we do, which is we take the log. So instead of doing the likelihood, we're actually going to do the log likelihood. Take the log. And it doesn't really matter what base we do. We're just doing a trick to sort of make things a little bit easier to calculate. And if you take the log of this number is quite nice. It's 9 times the log of 0.85 plus 1 times the log of 0.15. Okay, and then this one would be the same kind of thing. 9 times the log of 0.95 plus 1 times the log of 0.15. No, 95 and 0.05. Okay, and this is called the log likelihood, 0.05. Let's try to erase this again. Okay, 0.05. Okay, so that's the log. This is the log likelihood. There is one other trick that we do, is you'll notice every time you like add a coin flip, you're multiplying by another number up here, right? If you had, instead of having 10 coin flips, it wouldn't be the product of 10 things, it would be the sum, it would be the 11 things or 12 things or so on. And then when you do the logs, then those multiplications turn into additions. So this is adding up 10 things, 9 copies of this number plus 1 copy of this number, 9 copies of this number plus 1 copy of that number. So as you add more things, it gets bigger and bigger. To sort of keep it kind of level, not only do we do the log likelihood, we do the average log likelihood. So we add in one word, the average log likelihood. And to do the average, all you got to do is divide by 10, because there were 10 coin flips total. So this is the average log likelihood. It's averaged over the number of coin flips we did. We did 10 coin flips, so we divided by 10. So this is the average log likelihood. And in general, the formula is going to be, it's going to be the number of heads, let's call it the number of heads divided by the total. Yeah, why not? Let's write like a sum. Number of tails times the log of p hat for heads plus the number of tails divided by the number of heads plus the number of tails times the log of 1 minus p hat. So if p hat is the estimate for a chance of of heads, for heads to come up, the probability, I guess, is the secret word, then the average log likelihood given our observation. Okay, so this is the formula we have derived. And again, this formula doesn't just come out of the blue. It comes from simple sort of first year probability stuff. You guys with me so far? Any questions or comments? Where did this thing come from? Let's put it in Desmos. My favorite thing to do in life is to go home and sit at my graphing calculator and let's plot different things. So we want to do this. We have some number of heads. I guess it was 9. And then we had some number of tails, which was 1. And we can make this a little bit bigger so we can see. And then what did I say the formula was? The formula is heads divided by heads plus tails times the log. Let's do log of this thing p. Okay, it should be a p hat. I don't know how to do hats though. We're just call it p. Actually, let's call it x. We'll just let the computer plot it. H plus t times the log of 1 minus x. Okay, and this is showing us as a function of our estimate. So the x value here is the estimate, right? You give me some estimate between 0 and 1, and we're trying to make it as likely as possible. And this is what it looks like. So Bob's guess was 0.85, and Alice's guess was 0.95. So let's see, x equals, let's call this function L for likelihood, or log likelihood. And Bob's guess was 0.85, and their score was L of 0.85. And that was Bob. And then this was Alice, 0.95, comma L of 0.95. Okay, and you can see on the picture, it's not symmetric. This is the thing that I want to draw your attention to. Bob and Alice, Bob did a little bit better than Alice because this function is not symmetric. It kind of goes really crazy near 0 and 1, okay? And as you change the number of heads and tails, the shape will change. So if you kind of like, okay, don't make your number of heads negative. That's a no-no, but let's see what kinds of things we can do. Here, let's make the number of heads, let's make that 9 like it was before, and let's have the number of tails run around. So the number of tails can run around. And this function is measuring how good or bad your guess is given some data that you saw, okay? And so it seems like 0.85 is a better guess than the other ones because it's higher up, it's doing a better score, it has a better likelihood. Okay, let's go back to the situation we were in originally, 1, 9. So both Alice and Bob were not quite right. They were both wrong. They didn't have the best possible guess. So the best guess is not an 85 point or a 95 point. Does anyone think they can say what is the best possible guess? What would maximize your log likelihood? Where is the green function? Where is it the highest? 0.9. People are yelling that. Yeah, 0.9 is the best. And so let's draw that in as well. 0.9 and the likelihood of 0.9. There we go. So that blue dot is the best. And in general, the best possible guess will be the ratio you saw of the heads and the tails. So the reason it's 0.9 here is, in general, it will always be the best possible guess will be at the heads divided by the heads plus the tails. H plus t, and the likelihood of h divided by h plus t. So even if you change these to really wacky numbers, the best possible estimate you can do, let's turn off Alice and Bob here, is always this actual ratio. So you get this like funky curve. Why am I showing you all this? This is sort of the heart of the difference between linear regression and the regression we're doing, logistic regression. The main difference is we are using this log likelihood. Okay, so the log likelihood, you can write it like this. Another way you can write it is like this. So this, you can also write p times the log of p hat plus 1 minus p times the log of 1 minus p hat. And this is when the true value is p. So on average, this will be the average log likelihood. And this is the sort of loss function that we use in these problems. So I'm going to take this formula and I'm going to write it over here. I'm going to write it over here. The loss function, and it's also related to the log likelihood. So it's the average log likelihood. Log. Let me leave a space. Average log likelihood. Okay, and it's not just the difference squared. It's this funny formula. Oh, I guess it should go down here. Okay, I'm gonna put it down here. P times the log of p hat minus plus 1 minus p times the log of 1 minus p hat. And we sort of derived it for simple coin flips. So if the true coins are p and you think they are p hat, this is like how good or bad you're doing. This is how we can tell who is better. And this is exactly the analog. In linear regression, it's very simple. You take the difference squared. But now it's this funny thing with like non-linearities and like, you know, it goes all wonky near 0 and 1. And that is essentially our loss function. So the thing we are trying to maximize in this game of doing linear regression for probabilities, we're trying to maximize this average log likelihood. Okay. There is one thing that should annoy you about the board if you've been paying attention. So there's a mismatch between the left column and the right column. So we have this nice thing. It used to be a square function. Now it's this crazy function we came up with. But there's something wrong. Something's silly. Does anyone see what is the mismatch? Yeah. Say again? The variance. Oh, yes, this is great. I don't have a variance. Let me tell you the story with the variance. In this situation, the best possible guess you could do is mu hat minus mu and make that 0. So if you get the mu hat exactly right on, and then you have the irreducible variance. In this situation, there is no variance added on, but we just discovered the best possible guess. The best possible guess. The best possible guess is to get it exactly right, p hat equals p, and then you get this formula, p log p plus 1 minus p times log of 1 minus p. This thing is called the entropy of p, of let's say a coin with probability p. And you'll notice on the graph we had, like the best possible point is not at 0, right? And so there's this, no matter how good your guess is, you will always be off by this much. Your log likelihood will always be at best case scenario this. And that is the entropy. You will never beat the entropy. And this is kind of saying that coin flips are unpredictable. Even if you get it right on, there's still some unpredictability left. And so the formula, it doesn't explicitly have the variance. The variance is like the irreducible error. The irreducible error in this one is because you can never get it down to 0. You're always going to have at least this much entropy. If you're into information theory, entropy is also related to how much information is in the coins and this kind of thing. So that's the analog of the variance, and that is not the difference I was going for. There's actually like a dumb, silly mistake that this should be somewhere. All right, let me give you a hint. So let's draw this one. This was some square function. Let's draw a square function on the board. and see how things are different. So let's do some function like x minus 0.9 squared plus say 0.1. I don't know. So that was the kind of thing, the kind of loss function that we set in the first column. It's the square loss. You want to get down to 0.9. How close are you? We'll do the square distance. What is different about that versus the one we did? That's right. Yeah. I've been saying, optimize them, but this one I was like, get the biggest possible log likelihood, and that one we wanted the minimum possible loss. So log likelihood is the thing you want to make it as large as possible. The loss is like how bad you do. You want to make that as small as possible. And so if you want to put them on the same footing in your table, you need to add one word that everybody always forgets, or at least I always forget. So I always mean it to be there, but I always forget it. And it's the word negative, the negative. So the log likelihood is not a loss function. The negative log likelihood is a loss function. So the log likelihood, you want to maximize it. The negative log likelihood, you want to minimize it. That way it fits into our framework. So I'm just going to add minus signs everywhere. This comes from this idea of we want to minimize it. And similarly, the entropy, as written, is a negative number. The actual entropy is a positive number. So the negative of all this negative number is a positive number. I'm going to put absolute value signs to maybe not freak people out. That's the entropy of the coin is some positive number. And if you forget the negative sign, you'll mix up minimizing and maximizing. Okay, that is the loss function. I will actually pause for one second. In this course, I just said, look, we're doing the square difference. We're playing this game with the square. That's the rules of the game, man. But the square is actually the negative log likelihood of something else. This is also a negative log likelihood. Also a negative log likelihood. Does anyone know what random variable has a negative log likelihood that is the difference squared? Or maybe I should point to this one. Maybe that one will give you a hint. What random variable has this kind of mu hat minus mu squared? Well, negative that, right, is the negative log. If this is supposed to be the negative log likelihood, then the log likelihood is that. And then this is the log, so I should exponentiate it. I'll do e to the power of this stuff, right? And that should maybe look familiar to you. This is a Gaussian random variable. So the square loss is actually the negative log likelihood of the Gaussian random variable, and the negative log likelihood of a coin flip is this loss that we have over here. This loss is called the cross entropy loss. And it's gonna be our measure, just in the same way the square loss was our measure before, of how good or bad we are doing on our estimates. So that's the game. You got to minimize the cross entropy loss. Okay, this is it for those columns on the table, or those rows. And I think that is the hardest thing about this regression we're doing. This is called logistic regression. Maybe I should write that down. Logistic regression is understanding the loss function. I think that's the most important part. Then the reason is, once you get away from doing this like linear thing with the betas, this cross entropy loss term will be here forever. So when people do machine learning, you go to the big machine learning conferences, this cross entropy loss formula is on everybody's poster. Everybody knows the cross entropy loss. It's like the starting point for every single method in sort of classification. The rest of it, the linear stuff, that's going to come in a second. But this part will be here forever, even if the other parts you'd use a different method. Questions or comments about this? Okay, so let me tell you the next part. And this was in those videos. The next part is how do you make a formula? So in linear regression, we just had beta times x. And in logistic regression, we got to come up with a p hat, and we measure how good we're doing according to the formula. But what is the formula for the p hat? And it's a very silly formula. You might think it's very silly, which is the formula is. Okay, let me erase this and make room, and I'll just tell you what the formula. The formula is you just do beta times x once again. Okay, so in linear regression, you did beta times x. That gave you the mean, and then p hat, you do beta times x. But this should bother you because beta times x is not even a probability. Like it's not even between 0 and 1. So if you go and you do that, let's say I have a little thing here. Let me turn that off. Okay, so if I just plot y equals what is the name of the thing? The thing is called beta. Okay, I have to copy and paste it, I guess. So here's some data, and here's my guess. And I'm trying to estimate the probability. Well, my guess is not even between 0 and 1. Like my guess goes above 1 and below 0. So that's not good. So you could think of it in a very basic way. Is we start with beta times x. And this is bad because this is any number. We got to map it down to, must map it to 0, 1. And how do we map it to 0, 1? We just apply this function called sigma. And sigma is the sigmoid function, the sigmoid of x, which is x over 1 plus x with exponentials, e to the x over this. So this sigmoid function, it converts the linear estimate beta times x, which is like how big or small the effect is. It converts it to a probability in 0, 1. And that is what I did over here in the thing. So if you go to this plot, this is beta x plus c. I can change the value of beta to make it higher or lower. But the way to convert it into a probability is to turn on this. So that blue curve is converting the value of this red line into a probability. And it can either be very close to 0 or very close to 1. I can move around the line, and I can change its slope, and that'll change things. But the nice thing is that blue curve, that estimate for the probability, is always between 0 and 1. And that's the sigmoid function. And that is, when somebody uses logistic regression, they mean I am doing the cross-entropy loss, and I'm doing the sigmoid function. So logistic regression really means a combination of two things: sigmoid plus cross-entropy loss, CE loss. Those are the two big ingredients. And everything that we're going to do is going to be kind of similar to what we did before, but with these two changes. So we add the sigmoid function, we put that around the beta x, and we also do the cross-entropy loss instead of the square loss. Those are the two big changes. Everything else is kind of similar. We're going to go into more detail in a second. But I want to do a little bit of a detour. What is the deal with the sigmoid function? What are its properties? What is it actually doing? And to help us understand what it's doing, I have some exercises for you about the sigmoid function. Here are the exercises. So the sigmoid function, sigma of x equals e to the x over 1 plus e to the x, it converts any real number, small or large, positive or negative, to a probability. It's a probability conversion function. And I have some really basic questions about it. What is sigma of 0? Here's a fact. Sigma of plus 2 is 0.88. What does that mean about sigma of minus 2? All right. Simplify this crazy thing. The log. Oh my goodness. Sigma over 1 minus sigma of the log. What is that? OK, I'll let you guys think about it for a few minutes. This will help us understand what the deal is with this. Okay, who could use more time? Okay, let me add on a couple more minutes. I think it's worth it to get to know the sigma the sigmoid function. Okay, time is almost over. Put in your guesses, especially if you didn't get to the last one. You can put in like DNE or 1, 2, 3 or whatever, and let me know how far you got. But let's take a look at this thing. And once you kind of know the tricks for dealing with sigmoid, it gets a lot easier. Let's see what people said here. So sigma of 0, the sigmoid of 0 is 0.5. That's exactly right. I'm trying to think of what would be hard about this one. I don't know. Okay. Sure. So this one is 0.5. So we convert the number 0 into the number 0.5. Actually, let's draw a little graph. That's my favorite thing to do. Let's make a new one. So it's the function e to the x divided by 1 plus e to the x. And it looks like that. So it kind of smoothly goes. And at 0, it's 0.5. So it converts the number 0. 0 is like not positive or negative, and it's not more likely or less likely, it's equally likely, right? 0 on a scale is getting converted to a 50% probability. Very nice, very nice. Okay, let's go to this one now. Sigma of plus 2 is 0.88. What is sigma of minus 2? Let's see if people figure this out. It is 0.12, that is right, 0.12. Let's see, negative 0.88 is tempting, but wrong. And so only about half the people got this one right. That is 0.12. And you can kind of see this in the graph. Let's put in x equals, what did I say, 2.0. So x equals 2.0 is over there, and x equals minus 2.0 is over here. And if you look at it, it is perfectly symmetric, right? So if you take this whole thing and you flipped it around, that's why 88% chance becomes a 12% chance, right? They have to be complementary. And you can do it mathematically as well. So if you do it algebraically, you can see this property. So these are properties of the sigmoid. Sigma of x equals e to the x over 1 plus e to the x converts real numbers r to probabilities. Okay, and what I want to prove, I want to prove that sigma of minus x equals 1 minus sigma of x. This is a claim, and the proof is easy if you know how to manipulate fractions. So the proof, sigma of minus x is e to the minus x over 1 plus e to the minus x. Okay, so there's your fraction. I plugged in a negative, the negative of x, you got negative x, negative x. So if you start that and you have worked with fractions before, you might notice you can do some tricks to simplify it. What's the trick to simplify this fraction of e to the minus x?
Like 1 over e.
Flip it, 1 over e. Oh yeah, let's do that. Okay, I like that. 1 over e to the x. That's different than what I was going to do, but will be just as good. Okay, now what? I flipped it.
And then times it.
Yes, that's what I wanted to do. Times it by what?
Ex.
E to the x. Yeah, very nice. So times this by e to the x, and then you get 1 on the top. So e to the x over e to the x cancels. You get 1 on the top. And then you get on the bottom, you get e to the x plus 1, right? So 1 plus e to the minus x became e to the x plus 1, kind of like flip-flop. Okay, and 1 over e to the x plus 1, how is that related to the original sigmoid? Well, the original sigmoid was e to the x over 1 plus e to the x. So the original sigmoid is like you have e to the x, could be big, could be small. You're doing the ratio of e to the x to 1 plus e to the x. This is the other half. It's the 1 part, right? And so mathematically, you could write 1 as 1 plus e to the x minus e to the x, right? And then you could factor out the first bit is the 1, and then you have the leftovers, which are the minus e to the x over e to the x plus 1, which is the sigmoid. Okay, so what is this saying? It's saying that the sigmoid is converting to probabilities, and it's symmetric around 0. Symmetric. Let's say x equals 0. So positive numbers are higher than 50%. Negative numbers are less than 50%, and they're like complementary. Like 2 and negative 2 are 88% and 12%. Okay, and last but not least, there is the property over here. That was maybe the hardest thing to do. The log of sigma over 1 minus sigma. What is going on there? Did people get this one? 30% of people said it was x, and x is the right answer. Let's see what other interesting things we get. One. Yes, okay. This is the right answer. So this function, this is the sort of the inverse of the sigmoid. Let's do it quickly. So this is another claim. This is how you invert it. The ln of sigma of x over 1 minus sigma of x equals x. And once again, this is just manipulating fractions. So the top is e to the x over 1 plus e to the x. The bottom, what is the bottom of the fraction? It's 1 minus sigma of x. We did 1 minus sigma of x a little bit ago. The 1 minus sigma of x is 1 over 1 plus e to the x. That was a nice little property, right? 1 over e to the x plus 1, that turns out to be 1 minus sigma. So you got sigma, that's the e to the x part. The 1 minus sigma is the 1 part. All right, very nice. And then these cancel. Boom, boom, which is the log of e to the x. And this is just x. By the way, this ratio, if sigma is a probability, you might have seen this kind of thing before. If someone says you do the ratio p over 1 minus p, p over 1 minus p. So for example, if p is 0.9, you would do 0.9 over 0.1 to get 9. So if you go to Las Vegas and you say, I want to make a bet on something that has a 90% chance to happen, the people who give you the bet, they'll give you a bet with the odds, which are 9 to 1 odds. So this ratio is called the odds. And mathematicians work with probabilities, but in Las Vegas they work with odds. So sometimes you'll hear things stated with odds, 9 to 1 or 1 to 9, that kind of thing. And what this little formula is saying is that the sigmoid function is the log odds. So the log of the odds, let's say the log of p over 1 minus p equals x, if and only if sigma of x equals p. So if the odds are 9 to 1, and then the value of x should be the log of 9. So example, if p equals 0.9, then the ratio, the odds are 9 to 1, 9 to 1 odds. And the log odds are whatever the log of 9 is. I guess the log of 9 is pretty close to 2. The log of 9 equals x. So the sigmoid function, it inputs the log odds. The log of 9, and it will tell you the probability that goes with that is 90%. I guess the example I just did, if the log odds are exactly 2, so if x equals e squared, x equals 2. X equals 2. X equals 2. If the log odds are exactly 2, then the odds are e squared to 1. E squared to 1. E squared, let's see, is just a little bit less than 9. E is a little bit less than 2. So e squared is a little bit less than 9. And the log odds, the probability is of these log odds is 88%. 88%. Just a hair under 9. So it just is slightly less than 9. Okay. 88%. So, and this is what we're doing. So why is this so important? So in our logistic regression, this is how our logistic regression works. So we have these coefficients, the slopes, and in the ordinary regression, the slopes, we multiply them by the inputs, the features, the x's, and they tell you the actual value you're estimating. I think the value is 3 times 100 square meters. So I think the house will sell for $300,000. That's what you're doing. In logistic regression, you do the same multiplication, but you interpret the thing as the log odds. So you say like, you have some value. If it works out to 2, right? If you do this stuff and you get x equals 2, maybe the beta equals 3/2 and x equals 4/3, then beta times x equals 2. And this interpretation, beta times x equals 2, means I think it's an 88% chance to be in class 1. So this gets fed into the sigmoid function, sigma of beta x equals 88%. Okay, I'm going to put a hat over here. So this is a little example. And so this is how I want you to think of, or how one should think of logistic regression. We're taking what we did before, we feed it through the sigmoid function, and it converts values, which could be positive or negative, into log odds, and then the log odds get converted to probabilities through the sigmoid function. That's like what we are doing here. Okay, this is a little bit technical, but that's the idea of logistic regression. Questions or comments about this? One question you should ask yourself is, who decided that we should do sigmoid? Why sigmoid? Why not a different function? Could be like a nice line function, could be something else. Why is it a sigmoid? And there is a very nice reason. The sigmoid function plays nicely with the cross entropy loss. This is the reason the sigmoid plays nicely with the cross entropy loss. Sigmoid plays nice with the cross entropy loss. And to understand what I mean by this, and what does it mean that it plays nicely with the cross entropy loss, I have one more, the final mathematized question for the day, is how are we going to find these things? And remember, when we're doing the loss function, we want to find the minimum of the loss function. In order to minimize a function, it can be useful to calculate the blank, where blank is a one-word answer. And that is what I would like you to fill in over here. When we figure out what this blank is, we're going to calculate it, and we're going to see why the sigmoid plays nicely with the cross entropy loss. Okay, let me give you 1 minute. 1 minute to do that. Okay. All right, time is up. Let's see if you know the kind of thing that would be useful if you want to minimize something is to calculate the, drum roll, reveal. 8 people said derivative. That is right. That's what I'm going for. Let's see, did somebody write? Gradient also equally good. So those are both right on. I said derivative. Gradient is also perfect. The gradient or the derivative tells you if you should increase it or not. So if we're going to like least squares, if I turn on, here's the derivative calculation. If someone says the derivative of the loss function, how good we are doing, is negative 0.3, then I can make it better by increasing beta. So if I increase beta a little bit, I'll get a slightly better estimate. And I can see, I can also write how good I'm doing. I can increase a little bit. And you see the loss is going down. So when the derivative is negative, that means you're too small. Make your number bigger. And then if the derivative becomes positive, then I've made it too big. I should make it smaller. And so I should play with the value of beta until the derivative is 0. And if you set the derivative to 0, that is the absolute smallest value I can get for the mean squared error, is 0.887. Let's derive this. I'll give you the sort of punchline sort of quickly. Okay. So the punchline sort of quickly is the loss, the mean squared loss, is it's a y minus mu hat of x squared or in other words, it's y minus beta times x squared. This is the loss for 1 point xy. And if you do the derivative, so this is the loss, what I call the loss for beta. If you do the derivative with respect to beta, so dd beta of the loss, which has to be a gradient if you're in higher dimensions, well, you're going to get 2 times y minus beta x times x. So very nice, simple formula. Y minus beta x is how far off your estimate is, and x is how far away your thing is. So this derivative is actually nicely calculatable. What you do is you take the difference between the purple dots and the blue, and you multiply by how far out you are. So it really is like this purple dot is pulling on the blue line based on this difference. And the derivative being 0 means there's an equal force sort of pulling it down, it's pulling it up. That's the derivative being 0. Why am I telling you all this? Well, the thing I wanted to show you, I wanted to answer the question, why did they choose the sigmoid? So in the other one, it's a crazy formula. It's P, let me write it like this. Yeah, P times the log, the log times the log of p hat, and p hat is sigmoid of beta x plus 1 minus p times the log of 1 minus the sigmoid of beta x. Okay, that's the log likelihood. I need negative signs. So this is the loss. This is the loss as a function of beta. Okay, and this is a really ugly formula. Like the sigmoids are super ugly. They got e to the x's. You got the stupid log p thing. The sigmoid is ugly, and the cross entropy loss are ugly. But nevertheless, I will skip the details. If you calculate the derivative of the loss, a minor mathematical miracle happens, and the ugliness in the cross-entry loss with the logs and all this stuff, the ugliness of that cancels out with the ugliness of the sigmoid, and you get a nice formula. The formula is this. It is p minus beta x, p minus sigmoid beta x times x. So in other words, there's a miracle happens, miracle cancellation. The ugliness of the sigmoid cancels out with the ugliness of the cross-entry loss, and the derivative of the loss function of the cross-entry loss is the difference between the true value of p and your estimate times x. In other words, it mirrors this calculation. The loss function over here and the loss function over there, they have very similar derivatives. And that is the reason people chose sigmoid for this thing, is to make this kind of math work nicely. When you do a logistic regression in your computer, it uses the same derivatives as for regular regression. And I'll show you what that looks like in this little table. So here is the same kind of thing, right? Let me delete this red curve. So here I have data. These are class 0s and class 1s, the purple data points. If I want to try to find the best value of beta that works, so here is the value of beta. Oh, where is it? There it is. And I can move it up and down, right? I was doing that before. I can ask, is it better or worse by using the cross-entry loss? And I can try to find the minimum. And if I do the derivative, I can try to make the derivative 0. So here I should make it a little bit smaller. And here the derivative is 0. And the derivative being 0 means there's sort of an equal pull. These points are actually class 1. They have low probability, so we're pulling up over here. And here we're pulling down. When the derivative is 0, there's an equal pull up and down by that nice formula. It just depends on the difference between these two things and how far the x value is. Where x values that are very far away get an extra boost that values that are close to 0 don't get. Okay, so that is why this is the answer to the question, why the sigmoid? And this is like very roughly the whole story with logistic regression. Of course, in practice, we don't do it in one dimension. We do it in many dimensions. And then all of the same issues that we had before of going from linear regression in one dimension to multiple dimensions will apply. And we'll get to those on Wednesday's class. Any questions or comments about any of this stuff? All right, so we're going to stop there. Don't forget your draft of your project 1.